and get started then. I'm going to mute you all for the moment. Allow participants to unmute themselves. Yes. All right. So the first thing I'm going to do here is reverse my screen and take a little bit of a walk over into my kitchen. This is where I am, to show you a couple of things here on my counter. And it's not staged for class, it just happens to be this way. But I have my mixer, my can opener, and my magic bullet. And what these three things all have in common is that they all have spinning parts. Okay, spinning parts that turn on. The mixer itself is a variable speed mixer, so it can turn on and you can obviously change the rate, and it's going to go, you know, faster or slower depending on what you do. But you know, people who design such things or work with cars or any kind of an engine that has spinning parts, they have to think about the amount of force necessary. Like, you wouldn't want to put a motor for a lawnmower in your kitchen blender, right? For obvious reasons. You wouldn't want to put a car engine in a can opener. And that's because these different types of spinning things require different amounts of force, and what we'll learn is called torque, to supply the spinning motion that is required. So what we're going to look at for today, for starters, as we think about rotational kinematics, is acquiring a new and common language to think about those things. So I'm going to be switching over here to sharing my screen. I'm going to be sharing a whiteboard with you and then writing on this whiteboard. I'm actually working on a Microsoft Surface, so I'm going to be ejecting my Surface, and I don't know what this looks like in terms of, you know, the video with me. You're probably seeing my hand or my ceiling or something as I'm doing this, but I'm going to be writing on here. Okay, so what we're thinking about in this context is a particle that is moving around a circle. That does not look like a circle. Let's fix that right away. So a particle that's moving around a circle from, let's say, point A here to point B here. And this is a circle of radius r, so that's the same on both sides. And it's moving like this through a length L through an angle theta. And it takes it some amount of time, delta t, to do this. All right. So normally what we would say is, in linear space, we would just think about the speed in terms of how far it went. So we would call this like delta L over delta T as our speed, right? But what we're really going to be thinking about is how to transfer from linear space into angular space. And for this, we're going to develop a whole set of new equations based on a set of new variables. So that's what we're doing today, is looking at kinematics in rotational space or angular space. Not spaces, but okay, just space. So think back to September, when we began thinking about kinematics as a whole. We thought about three different kinds of kinematic quantities: position, then velocity, then acceleration. And as I'm going along here, you can kind of fill in what you know in the table that I'm kind of building here. I'm going to write out the variables and then also the units next to that in a different color. So what variable did we use for position in linear space? Somebody just hit your space bar and say it.
X.
X.
Great. How about velocity?
Like
V.
Seconds.
V. Oops. Doesn't look like a V. Let me fix that. And acceleration?
A.
A. All right, so let's now do the units for these three things in linear space. So the units for position in linear space were
Meters.
Meters.
this, velocity,
Meters over seconds.
good, and acceleration.
Meters per second squared.
Great. Can't draw an S for some reason. Okay. All right, good. So now what we're going to do is transpose these over into a new space. And then we'll talk about the relationships between this and rotational or angular space. So in angular space, our position variable is going to be theta. So you're familiar with theta. We've talked about theta before when you're talking about inclined planes and all that. It's a very common variable that is used to describe an angle. We'll come back to the units in a moment. For velocity, we're going to introduce a new variable. Oh, excuse me one second. I need to manage participants here. I think I need to admit TO. Okay. All right, let's fix that. So velocity is a new variable. It looks like kind of a curly W. And angular velocity is called omega. Okay, so it's a lowercase omega. An uppercase omega looks different. You might know an uppercase omega looks like this. We're not using that though. Okay. And angular acceleration is another variable. It is alpha, fishy looking thing. So the alpha and the omega. The units here are different as well. The units, instead of for angle using degrees, we're actually going to be using radians now. So you're familiar with radians from math class, and just to remind you that there are 2 pi radians in 360 degrees. Okay, that's something everybody knows. For omega then, angular velocity, can anybody imagine what those units might be for angular velocity? If the position variable is radians.
Radians per second squared.
That's for angular
Oh,
acceleration.
shoot. I mean, radians per second.
Perfect. Yep, radians per second. And then this is radians per second squared. Great. Okay, so that establishes our kinematic definitions. And we're going to come back to thinking about, what about the idea that we had a centripetal. We'll come back to thinking about that later, because right now, actually what we're thinking about when we're thinking about acceleration is this is a tangential acceleration, right? We're thinking about a spinning blade or something turning that's getting faster or getting slower, not what's confining it into the circular path. So this is later. We'll come back to this, okay? But right now, though, what I want to do is now that we have this vocabulary established, let's put it into some sentences. So I'm going to be clearing these drawings here, okay? And using these in terms of kinematic equations. And again, I'm recording this so you can look at it later. Also, I have uploaded stuff from my Rocket Book notes that you can see in the folder, and I'll put on Google Classroom a reminder to that. So let's recast our old kinematic equations that we had that were on that backboard in my room into rotational space. So in linear space, we used to say V equals V naught plus AT, but now in angular space, if we're talking about the speed of a spinning blade, we can say omega, which is the rotational speed, equals omega naught, its initial rotational speed, plus alpha t. What that means is if you have something that's slowing down, for example, that you might be able to think about what is, if the final speed is 0 and you know what its initial speed is, if you have an angular acceleration of a certain amount, how many radians per second squared it's slowing, you can figure out maybe how much time that's going to take for that item to come to a halt, which might be useful, okay? So let's move on and think about other equations that we had. You'll remember this one, the long one, x equals x naught plus v naught t plus 1/2 AT squared. And that we're going to be casting over into angular space, remembering our position variable was theta, and then we come to a screeching halt here for a second, say theta naught really doesn't have a meaning, right? Because we go back to thinking about that circle I drew earlier, circle of radius r and an object moving from here to here, that we do have a theta, but what is theta naught? It really is definitionless, okay? There isn't a theta naught because you just move around and around this circle. So we're always going to set that equal to 0. So there won't be a value there for that. So we move to the next term, which is v naught t becoming omega naught t, and that's our initial angular velocity times how much time? Plus 1/2 alpha t squared. And then the last really useful kinematic equation that we had was the v squared one, which we used a ton. Let me hang on a second. I got a problem down there. Let's get rid of that. Okay. V naught squared plus 2ax minus x naught, which in angular space becomes omega squared equals omega naught squared plus 2. And notice that, you know, we have a turning into alpha, but x minus x naught is simply theta, okay? Just that position, how much it moved. Okay, let me pause there for a second and see if you've got questions about what we've done so far. No? Okay, before we go on and try doing a problem together with stuff like this and see how that would be contextual, let me say another thing or two about this idea. I'm going to keep redrawing this circle over and over again. Again, this is one object that is moving around the circle, an arc length L subtending angle theta, and that radius of the circle is R. Based on definitions that you know in math, you know that theta, that angle subtended, is equal to L over R. That's just a definition. But this is also going to govern, if we're thinking about the particle moving, if we think about what the linear velocity is, v equals delta L over delta t, as I said in the very beginning, we can now think about how we might relate the linear velocity right here. Whoops, didn't mean to do that. Relate that linear velocity to the angular velocity omega, okay? Because these equations, these kinematic equations, just talk about what's going on in either space. This is entirely angular, this is entirely linear. But what if we knew, for example, a linear velocity and we wanted to translate to angular space, and we'd have to do something different? Well, what we're going to do is use this in a substitution right here, and we can find out how linear space and angular space translate to one another, okay? So knowing that theta equals L over R allows us to substitute in for L there. So we would find that V is equal to delta R times theta over delta T. And if R isn't changing, okay, so if you're at a constant radius outside the circle and you're not spiraling in or spiraling out, then you can kind of factor R out of there. You get R equals delta theta over delta T. And does anybody see what is happening there on the right side if I circle this in red? Let me see. What is this? Delta theta over delta T. The change in angle as a function of time. Anybody want to take a guess?
Centripetal force?
Nope.
Velocity?
Yeah, which kind of velocity? What's the variable?
Omega.
Yeah, it's omega. Excellent. All right, so this is actually R times omega. Delta theta over delta t is the definition of omega because omega is angular velocity, and that's how much angular position has changed as a function of time. Very cool. All right, so this means that, I'll just put it in red, the whole thing. The way that we connect angular space to linear space for velocity is like this. And we can do the same thing. Oh, I don't know what just happened there. Okay, we can do a similar thing with acceleration too. Because if we're thinking about the tangential acceleration, right? Meaning acceleration of that point if the blade is speeding up or slowing down, that's really the change in v over the change in t. Acceleration, that's just a definition. But if v is r times omega, we can substitute this in r times omega over delta t. And again, if r isn't changing, we factor it out. Does anybody see what's happening there? What is this little thing? Delta omega over delta t, the change in,
Alpha.
yeah, it's alpha. Cool. So the tangential acceleration is just r times alpha. So I'll write that in red, and then we're going to transition to something else. Sorry, it's kind of crowded. So the tangential acceleration is r times alpha. Okay, I'm going to switch over and stop my share here of that for a minute. I'm going back to sharing my screen in a different sort of way because I want to show you a little video I made yesterday. So if I was in my classroom, I would be showing this to you on my turntable, which you'll remember we used during the centripetal force unit. I think I had like a duck going around in a circle. Oh, Ian's coming to class here. Here he comes. All right, so I'm going to share this little video with you. If I can find it. Hang on a second, maybe not. I've got to get this here. Sorry, it's a little clunky. All right, here we go. All right, so you should see, and I'm working with limited resources here. You should see a thing of Tic Tacs on a turntable. You guys see that? Okay, my question about this is, which item is moving faster, the Tic Tacs or the watering can?
The Tic Tacs, there's a greater radius.
Okay, anybody want to counter that?
Aren't they moving like the same speed?
Okay, and is that Ibrahim? Explain what you mean by that.
Because like they're on the same, it's not like there's two different disks that are spinning at different speeds. They're on the same disk that moves the same amount. As
Okay.
in like there's one.
It depends on if you mean angular or like actual speed.
Okay, I asked a terrible question, right? My terrible question was, which one's moving faster? And both of you were right. I think that was Jack and Ibrahim that answered that, I think. You're both right, okay? You're both right because we can talk about two different speeds. We've talked about two different kinds of speed today. We've talked about the angular speed and we've talked about the linear speed, right? So in terms of angular speed, they both are going at the same angular speed, but the tic-tacs are going at a higher linear speed because they're traveling more distance in the same amount of time. Everybody understand that? I hope. All right. I'm going to go back to a screen share for a whiteboard for our last 5 minutes here, and we'll do a sample problem with this sort of thing. We're going to take a look at thinking about a blender. Okay, so let's think about a blender that is rotating at a high rate of speed. So I have to check my screen again here. A blender rotating at 6,500 RPM. What does RPM mean?
Rates per minute.
Yep,
Revolutions per minute.
revolutions per minute.
Yeah.
So the blender starts rotating initially at 6,500 RPM, and it's going to halt, it's going to halt in 4 seconds. And we want to know what the angular acceleration is. All right, so we know already that that's going to be a negative angular acceleration because it's coming to a halt. So we have to actually do 2 things here when we're solving this problem. The first thing we have to do is convert the RPM into radians per second. All right, so that's our first order of business here. And this is just a unit conversion. So we're going to remember that we have 2 pi radians in each rotation as we're doing this. So this is rotations per 1 minute. And we're going to be converting that over into radians per second. Okay, so we're trying to fill in this blank here. So just in the interest of time, I'm going to do this really quick. So we have 2 pi radians, and radians are sort of a unitless thing, right, for rotation. So that's going to take care of this. And then we also know that each minute of time is 60 seconds. So if we're converting that and multiply everything out, we should be getting around 217 pi. Okay, and you can also multiply that. Sorry, that's a little scrunched. And our second step is then to choose, as we've done before, choose the right kinematic equation, choose a KE, and substitute and solve for the missing quantity. So in this case, we have the initial rate of rotation, we have how much time it's taking, and we know that it's coming to a halt. So we know omega naught equals 217 pi radians per second. And we know omega final is 0 because the thing's coming to a halt, and that the time it's taking is 4 seconds. So if you plug all of those in and solve for alpha, you'll get negative 54. Oh my gosh. Eraser, come on. I need some lessons on how to use this properly. All right, negative 54 radians per second squared. All right, so we are at 10:43 a.m. You will see that on Veracross, I put up a problem set for you. So what my intention is with the problem set is that you can take as much time as you need this week coming to work on that problem set. And it's only 6 problems anyway. So I'm hoping that on Monday or Tuesday, I think it's Monday we have class, right? On Monday, if you have questions about this stuff, that you can pop on and ask them if you want to work on those problems at that time, you can do that then. But I won't be having like a formal class like this. It would just be optional for you. Okay? That's all I have for you today. Have a great day, everybody. Bye.
Bye.